There's a strange problem with modern roads. They look strong, they feel permanent, and they cost billions of dollars to build. But give them a few decades, sometimes less, and cracks start creeping in. Asphalt begins to crumble, repairs become routine, entire sections get rebuilt again and again like a never-ending cycle. Now compare that to something built over 2,000 years ago. A road laid down when empires were still figuring out how to unify themselves. Still exists. Not just fragments, not just ruins, entire sections, still recognizable, still structurally intact, still resisting time in a way modern infrastructure struggles to match. And it wasn't built with machines. No concrete mixers, no steel reinforcement, no computer models, just dirt, fire, water, and an understanding of physics that feels almost unsettling in how accurate it was. It starts with a decision that sounds almost extreme. Instead of building on top of the earth, these engineers decided to change the earth itself. Because the biggest enemy of any road isn't traffic. It isn't weather. It's something much quieter, something alive. Roots push upward through tiny cracks. Seeds slip into gaps and expand season after season. Insects dig tunnels underneath, weakening the structure from below. Moisture seeps in, feeding everything that slowly breaks the road apart. Modern engineering fights this with chemicals, constant maintenance, and periodic resurfacing. And even then, the battle never really ends. But ancient Chinese engineers approached it differently. They didn't fight life, they removed it. Workers would dig down until they reached stable ground. Then came something unexpected. Fire. Not small fires, but sustained heat intense enough to completely transform the soil. Moisture was driven out. Organic material, seeds, roots, microorganisms, was burned away or destroyed. What remained wasn't ordinary dirt anymore. It became something closer to a hardened, compacted layer that behaved almost like a primitive ceramic. Dense, dry, resistant to intrusion. Then came compaction. Layer after layer of earth was pounded down using tools and repeated force until the particles locked tightly together. This wasn't loose soil anymore. It was engineered ground. What formed at the base of the road was essentially a dead zone, a layer where life struggled to return. And that changed everything. Because without roots breaking through, without insects tunneling underneath, the road stopped being something nature could easily consume. On top of that base, another layer was added. Rammed earth, compacted to near maximum density. Each layer carefully pressed, creating a surface that was harder than the natural ground around it. Then came one of the simplest but most overlooked details: water. Water destroys roads slowly but relentlessly. It seeps in, sits in cracks, expands when it freezes, softens the ground beneath, and eventually causes collapse. Instead of trying to block water completely, these engineers guided it. The road was built slightly higher in the center, sloping gently toward the edges. Rainwater naturally flowed outward instead of pooling. Ditches along the sides carried it away before it could do damage. 3 layers, 3 defenses. Remove life, increase density, control water. That combination allowed something incredible to happen. Time passed. Decades turned into centuries. Dynasties rose and fell, and the road stayed. But building a durable road was only part of the problem. An empire isn't held together by stone alone. It's held together by movement. Messages, armies, supplies, everything needed to move quickly across vast distances. Without speed, even the strongest empire becomes vulnerable. So the solution wasn't just to build a road that lasted, it was to build a road that improved itself over time. That idea sounds impossible at first, but it started with a simple rule. Every cart in the empire had to be built the same way. The distance between the wheels, the axle width, was standardized, roughly 5 feet across. No variation, no exceptions. At first glance, it seems like a logistical decision. Easier repairs, interchangeable parts, faster manufacturing. But the real effect showed up on the road itself. When every cart has the exact same width, every wheel follows the exact same path. Over time, those paths become grooves, ruts carved into the surface. Normally, ruts are considered damage, signs of wear, something to fix. But here they became part of the design. As thousands of carts traveled the same tracks, their weight pressed down repeatedly on the same lines. That pressure compressed the soil even further, increasing its density beyond what builders could achieve during construction. The road wasn't wearing out, it was being reinforced. And there was another layer to it. Many of these wheels had iron components. As they rolled through the grooves, they scraped and smoothed the surfaces. Loose particles were removed, irregularities were flattened. The road was being polished. Every journey made it stronger. Every mile traveled improved the structure. It was, in a very real sense, a self-maintaining system. And that changed how maintenance worked entirely. Instead of sending crews to constantly repair damage, the traffic itself became the maintenance force. But speed still depended on something else. Horses. A horse can move fast, but not for long. At high speed, exhaustion sets in quickly. Push too far, and the animal collapses. So even with a perfect road, long-distance travel had limits, unless the system changed, and it did. Along the road, small fortified stations were built every few miles, each one stocked with fresh horses, supplies, and personnel. A rider carrying a message would arrive, dismount, and immediately switch to a new horse. Within minutes, the journey continued at full speed. The exhausted horse stayed behind to recover. This created a relay system. Instead of one horse traveling hundreds of miles, dozens of horses each handled small segments. The result was speed that felt almost unnatural for the time. Messages could cross vast distances in days instead of weeks. But these stations weren't just about speed. They were checkpoints. Every movement was observed. Every traveler could be monitored. Information flowed in both directions. The road wasn't just infrastructure, it was control. And building it required something else entirely: scale. Hundreds of thousands of workers spread across enormous distances, each one needing food, tools, and coordination. Supplying that many people in remote areas, especially mountainous regions, sounds nearly impossible. But the solution was built into the process itself. Construction didn't happen all at once. It moved like a wave. Sections were completed step by step. As soon as one part was finished, it became a pathway for supplies to move forward. Food, materials, tools, everything traveled along the newly built segments to reach the next construction zone. The road was feeding its own creation. It expanded forward while supporting itself from behind. But as the terrain changed, so did the challenges. Flat land was one thing. Mountains were something else entirely. And ahead stood barriers that couldn't be compacted, leveled, or simply built over. Solid rock, massive ranges, vertical cliffs. No amount of packed earth could solve that. So the approach changed again. Instead of working around the mountain, they began breaking it apart. Mountains don't negotiate, they don't compress, they don't shift easily. And when ancient engineers reached massive granite ranges, the kind that rise like walls across entire regions, the problem changed completely. Bronze tools weren't enough, not even close. Granite is incredibly hard. Trying to carve a road through it using basic tools would take lifetimes. So instead of trying to overpower the mountain, the engineers used something far more effective. They made the mountain break itself. The method sounds simple, but the execution was brutal. Fires were built directly against rock faces, not quick flames, but sustained, roaring heat that lasted for hours, sometimes days. The goal wasn't just warmth, it was transformation. Temperatures climbed high enough to force the rock to expand. But granite isn't uniform. It's made of different minerals, each reacting to heat in its own way. Some expand faster, others slower. That mismatch creates stress inside the rock, invisible at first, but building. Then came the second step, sudden cooling. Water was thrown onto the heated surface, causing an instant drop in temperature. The outer layer contracted rapidly, while the inside remained expanded. That tension had nowhere to go, and the rock cracked. Sometimes it split cleanly. Sometimes entire slabs peeled away, as if the mountain was shedding its own skin. What tools couldn't carve, physics shattered. In tougher sections, the cracks were pushed even further. Wooden wedges were driven into the fractures, then soaked with water. As the wood absorbed moisture, it expanded slowly but with incredible force. Cracks widened, blocks broke free, ton after ton of stone, removed without explosives, without steel, just through an understanding of how materials fail under stress. But even after cutting through mountains, another problem appeared. Some places didn't offer ground to build on at all, just empty space. Deep gorges, vertical cliffs, drops so steep that looking down felt like staring into nothing. No foundation, no stable surface. For most civilizations, that would be the end of the road. Here it became something entirely different. A road in the air. Workers were lowered down cliffs using ropes, suspended hundreds of feet above rivers. With wind pushing against them, they began carving holes directly into the rock face. Each hole was carefully shaped, deep enough to hold weight, slightly angled upward. That detail mattered more than it seemed. Into those holes, thick wooden beams were inserted, strong, heavy timber extending outward from the cliff, hanging over open space. Then planks were laid across the beams. A walkway formed. At a glance, it looked fragile, temporary, almost impossible. But the real strength came from how it handled force. When weight was placed on the outer end of a beam, a person, a horse, a cart, the beam tried to rotate downward. But because it was wedged into an angled socket, that rotation pushed the inner end harder against the rock. More weight meant more pressure meant more friction, and more friction meant a stronger hold. The heavier the load, the tighter the beam locked into place. It didn't weaken under stress, it reinforced itself. That's the kind of insight that feels modern, something that would come from advanced calculations or simulations. What's being built now that will still be here 2,000 years from now? Because eventually everything becomes a test of time. Not just whether something works, but whether it lasts. And those ancient roads didn't just survive, they refused to disappear. If this kind of deep dive into ancient engineering and hidden innovations is something worth exploring further, make sure to subscribe and stay tuned for more stories that uncover how the past solved problems that still shape the present.